Hello everyone and welcome to today's lesson on the diodes and the DR2 port networks. Today we're going to study a two-terminal nonlinear device known as diode and two of its applications that can be found in electronics. The diode is a semiconductor device So it's a semiconductor device that has a PN structure. This means basically that we have a PN junction here. In practice, both P and N regions are part of the same silicon crystal, doped with acceptor and donor impurities. What do I mean by this? Well, both P and N regions are part of the same silicon crystal, doped with acceptor and donor impurities. Let's go ahead and take a look at just how such a PN junction looks like. And if we quickly search on the internet, you'll see this schematic, which is best for our purposes. I'm just going to copy this image and post it here. So this is exactly what I stated above, the P and N structure of the diode. To the left of the structure we have the holes, and to the right we have the electrons. These holes and electrons are what we call acceptor and donor impurities. Very simple. So the connection between the diode and the outer medium is realized via aluminum contacts, one connected to the N region and the other to the P region. So the contacts between the diode and the outside world realized through aluminum contacts, one connected to the N region called anode, and the other connected to the P region known as cathode. Okay, so this is another very important detail about the diode, namely the anode and the cathode. So basically, the diode, we can say that the diode is a two-terminal device because it has an anode and a cathode. The general symbol for the diode, I can draw it or I can just search it here. If I quickly do a search, this is perfect. You'll see that it looks a little something like this. To the left we have the anode and to the right we have the cathode. Now there are some measurements that we need to take into consideration when we talk about the diode, namely the current and the voltage. The current through the diode is like this. We know that the current goes from the left to the right of the diode due to this arrow here. This little bar or line, if you want, shows us the direction of the forward current flow. So we know that the current across the diode goes from anode to cathode. And it's the same thing with the voltage, because wherever we have a current, we also have a voltage. And the voltage drop across the diode, VD, is marked like this. And again, the voltage is from anode to cathode. Please note how I wrote these dimensions, the current and the voltage. So whenever we work with these dimensions, the current and the voltage across the diode, and not just the diode, we write first a lowercase letter, and then this lowercase letter is followed by a capital letter, which basically shows us kind of messed up there. Which basically tells us which device are we talking about. So going forward from the ideal model of the diode, we have to discuss about how this diode behaves. Before we can talk about the behavior in a real world of the diode, first we have to consider the simplest model of the diode. So to do that, you can think of the diode in its ideal state as a switch. Capital letters because this is very important. So you can think of the diode in its ideal state as a switch. How does this behavior look like? We're going to explain this right now. So like I said, you can think of the ideal diode as a switch, meaning it has two states. Which are those states? The on state and off state. Very simple. So let's go ahead and draw the model of the ideal diode for both the on state and the off state. So on state, our ideal diode will look a little something like this. So to the left we have the anode, and we have a switch. Like this. This is the ideal diode in the on state, and in the off state our diode is basically an open circuit like this. Okay, so let's go a little deeper into this and see what happens in each case in terms of current and voltage. So whenever the diode is on, or whenever we consider the diode to be on, we think of there being a current going through the diode. So the current across the diode is greater than 0, and the voltage, because we are considering the diode in its on state, should be equal to 0 in the case of the ideal diode. And when the diode is in its off state, we have no current going through the diode, and the voltage across it is less than 0. So then our VTC, which stands for voltage transfer characteristic of our ideal diode, will look a little something like this. If I can make a little bit more room. Okay. So this is the y-axis. This is the x-axis. However, as you'll soon see, these two axes are actually not y and x, they are current and voltage. So for the off state, the VTC looks like this. And then it climbs straight up like this. This line, this y-axis, is the current. So if you want ID, okay, the current through the diode, and the x-axis is VD, the voltage across the diode. And you'll notice that the change between the off and on state occurs at the 0 point for the ideal diode. This 0 point will be called threshold voltage. It's basically the point where the diode enters its conduction state. But but as you'll see later, the VTC in real life terms is never 0. It always is higher than 0. Generally speaking, it is 0.7 volts, 0.6, 0.7 volts, but we'll discuss about that later. Now that we know how our diode behaves, we have to also separate this graphic into two regions. The forward bias to the right, this is where we consider the diode to be on, And to the left we have the reverse bias. Where we consider the diode to be off. So these are the two states of the diode, and generally speaking, this is the voltage transfer characteristic. And let me explain a couple of things, especially what's the deal with this VTC and why that is important. To understand more about the VTC, we have to discuss about switching DR to port networks. Okay, so switching DR to port networks. A circuit with two ports is called a network, and this DR two-port network is also called a DR because it is composed of a diode and a resistor. The general model of such a network looks like this. So we have a voltage source that is connected to the input of our DR two-port network. And this network is connected to the output. And we measure the output here to the right side of the network. So this is VI input, and the output is here. Eventually we'll also connect something called a load resistor. We'll discuss what's the deal with about this load resistor later. But let's comment on every single term of the switching DR two-port network. First of all, switching. Why is this switching? Because of the diode. Like I said, the diode can be in two states. It can be on or off. Because of the fact that the diode can change its state, we say that this network is a switching network. DR two-port. DR, D and R. D comes from diode, and R comes from resistor. So we have a circuit that's composed of a diode and a resistor. And two-port because we have an input port, this one, and an output port. And this entire thing is basically a network because we have input, output, and the DR block all connected, making a network. Now, when working with DR two-port networks, we have to remember that these networks operate, or if you want, these networks are driven by voltage. And because these networks are driven by voltage, we discuss about a voltage to voltage system where the input is a voltage and the output is a voltage as well. So this is the input and this is the output. And because both the input and the output are voltages, we refer to the behavior of this DR two-port network as VTC, otherwise known as the voltage transfer characteristic. Very simple stuff to understand. So let's go ahead and solve one small exercise and see let's see how we can find out the VTC of the ideal diode. So we'll write here, consider the following two-port DR network with an ideal diode. Okay, so I'll copy this image. No, not this image. We'll just do this instead. So easier. There we go. Okay, there we go. This is how two-port DR network looks like. And we have to plot the VTC. So that's our task, to plot the VTC. How do we solve this? Well, like I said, we have to consider the on state and the off state of the diode. There's actually an entire algorithm that we have to take into consideration. First of all, we have to consider the two states of the diode, the on state and the off state. For each state, both on state and off state, we can draw an equivalent circuit. And because we stated that our ideal diode behaves like a switch, basically the diode itself becomes a switch. Only we also keep the anode and the cathode in the circuit as well. So this is the equivalent model for the on state and the equivalent model for the off state. I'll draw it here. Anode, cathode, and a resistor. At this point, we don't really care about the resistor because we are only interested in seeing what happens from a theoretical standpoint. Okay, so these are the two states of our diode. Now that we have the states of the diode and we've also drawn the equivalent circuits, we can start to consider the behavior of these circuits based on how the diode behaves. So for the on state of the diode, our diode becomes basically a short circuit. So this is important. The diode becomes short circuit. And for the off state, it's the complete opposite. The diode becomes an open circuit. Okay, the voltage, the output voltage, which is measured across the resistor for the on state, will be equal to the input voltage. So V0 will be equal to Vi. Because, remember, the diode is a short circuit. Meaning, basically, we have a wire here. So this voltage source and the resistor are connected. But because the diode is basically a short circuit, I think I wrote it wrong. So for the it's actually the other way around. For the off state of the diode, the output voltage is 0. The output voltage is 0. So let's go ahead and write this. The output voltage is 0 for the diode if it's in the off state, and for the on state, I wrote it correctly the first time. It is Vi. It is equal to the input. So this is what happens to the output voltage in the two states of the diode. Here we don't have an output voltage because the diode behaves like an open circuit. Now, in terms of current, the current through the diode, for when the diode is in the on state, we have a current going through it, which is greater than 0. Even if this is a wire, there's a current that goes through this wire. The same thing cannot be said about the off state of the diode, because the current through the diode here will be 0 due to the diode being open circuit. So we don't have a voltage, an output voltage or a current through the diode for the off state, but we do have a voltage and current for the on state of the diode. For the on state, the current that flows through the Vi, the voltage source, and the resistor has the following value. And this relation is basically given by Ohm's law. Which in case for the output, which in case for the resistor states that VR is equal to the current through the circuit multiplied with the value of the resistor. And thus we can obtain the following relation. The diode current, which is the only current that flows through this circuit, will be equal to the input voltage over the value of the resistor. And thus it results the following two conditions. The input voltage should be greater than 0, of course. You cannot divide by 0. And the output voltage should be equal to Vi, which is the same condition as stated here. So it's basically the same thing. For the diode in the off state, we have Kirchhoff's voltage law, which tells us the following. The voltage across the diode is less than 0, and also Vd can be written as Vi minus Vo. because if you remember, Kirchhoff's voltage law basically states that the sum of the voltages around a circuit should be equal to 0. So from that, we can obtain this relationship, this second one. And these two relations then give us the condition of Vi being less than 0, okay, and Vd should be equal to 0. So these are the these are the four things that that interest us most. And with these four expressions here, we can then draw the VTC, and you see this time it looks a little bit different from what I presented to you before. Okay, a little something like this. The x-axis and the y-axis. I lost the mouse there a little bit. Okay. And our VTC looks a little something like this. Okay. So for when the diode is in the off state, the voltage should be less than 0. And the input voltage should be less than 0, and the voltage across the diode is equal to 0. And for the on state, the output voltage is equal to the input voltage, which means that our VTC is no longer a straight line that goes up, straight up on the y-axis, but it's rather in diagonal. And this is as a point of reference between the input and the output voltage. So you can say here that VO is on the x-axis and VI is on the y-axis. This is VO, by the way, it's not VD. So this graph, and there was another graph that we draw, and this one, these are the two graphs that really interest us the most. This is the behavior of the ideal diode. This is in terms of voltage and current, and this is in terms of the input and output voltages. So that's pretty much all there is to it to discuss about the diode, the ideal diode, from a theoretical standpoint. And now let's consider a couple of exercises. So this time we're not going to work on paper, but rather we're going to work with a simulator called LTSPICE to solve these two simple exercises. So we're given this following DR2 port network with R1, so telling us that it's 1 kilo, and a diode 1N4148. In real life, we cannot work with ideal components, which is why I have chosen a real model for the diode. If I open LTSPICE, which is this here, we can start to build our circuit. So we have a voltage source, V1, that is linked to a diode, Control R to rotate it, And this diode is of course linked to a resistor. Just press R on the keyboard if you want to get a resistor. It's very simple. So this is our circuit. And of course we cannot forget about the ground node, otherwise the simulation will not work. Okay. So for our diode we'll pick 1N4148. The model of the diode that we said we were going to use. We'll say a 1 volt. We'll give 1 volt input to the circuit, and our resistor states here that it's 1 kilo, but we're going to use a 124 ohm resistor instead. So let's create a simulation profile. Click on this running man icon, and then you'll be brought up to this menu. We are interested in DC sweep, and we want to sweep the first voltage source V1 in a linear fashion with values between 0 and 12 volts. So start value 0 volts, stop value 12 volts with an increment of 1 volt. And you'll see that our simulation pane already opens. So of course we're interested in the output voltage. So let's measure it. And this is how the output voltage looks like across our diode. We are now using a 124 ohm resistor. And let's go ahead and make a couple of measurements on the graph and see what happens. First, you'll notice, like I stated before, it's not a perfect straight line. And this is what we get for a DC sweep. So this is the output voltage across the diode when we perform a DC sweep analysis. So voltage to voltage. You can see the x-axis is voltage and the y-axis is also voltage. If we go to the left of the diode and we click here, this is what the input waveform shows us, the blue line. So this is the input and the pink line is the output of our circuit. So let's perform a couple of analyses. We have to find the current through the diode. So to do that, we'll close that, reopen the simulation, and right click on the diode itself. So we get a voltage to current characteristic. And we can click on the icon of our output voltage to get a cursor. And we can use this cursor to navigate around our output characteristics and find the values that we need. So for a current of 4.2 milliamps, so we're looking at the vertical block here. So 4.2 milliamps, that's very, very low. 4.20, I think. No, 4.02. So it's even lower. I can't quite catch the value, so I can zoom in on this area. Maybe that will help us. So 4.060403. There it is. 1.14 volts. If I copy this table, if it'll let me, and take it to OneNote, something like that, only a little bit better. So actually I'll delete that because it's very bad. Okay, so let's go here and put it here. Nice. So for our 4.02 milliamp current, we said that we have a 1.14 voltage. Now we have to measure for 6 milliamps, which is even lower than the previous value. So 6.54. We'll have to zoom back in. Up a little bit. 6.54, 1.47 volts. And I'm just going to do the third one as well. Then I'll leave you these three as homework. So for 7 amps, 7.01, if I read that correctly. Can't quite measure them here. I'll have to zoom out a bit. 7.01, 1.53. So it's basically you basically have to perform this analysis 3 more times to find the values for the output voltages in this case. Okay, so I'll leave that to you as homework. And the next task asks us to measure the output across the diode for a negative DC sweep, so -12 to 0 volts. So we have to change the parameters of our analysis. We're starting at 0 and going down to -12 with 1 volt increment. Again, we're interested in the current, and you'll see that this is how the output waveform looks like this time. So it drops from 0 nanoamps, and it reaches 1. It reaches a value which I think is, I don't know, we'll see. But here we're working with negative voltages. In real life, this thing cannot happen. But anyway, if we go ahead and perform and put on our cursor, we can see that at the end of the day, the output of the diode, so the output current through the diode, is somewhat stable at -2.52 milliamps. So there's really nothing for us to analyze here. So starting from -1 volt to infinity, it's stable at -2.52. So if we are to perform any kind of sort of analysis, we have to perform them in the frame to the left side here, between 0 and -1 volt. This is where we can perform any sort of analysis. And if we are to stick with the table thing, for minus 837.58 picofarads. So minus 8 too much, 8.30. You cannot catch the value here either. So I'm just going to go with the next best thing. Minus 838.13 pico amps. We get a minus 332.46 millivolts. So we can write them here. If we go further, for minus 1 nanoamps, it's minus 396.67 millivolts. You could write it here. And for minus 1.19, go further down, is minus 475.28 millivolts. Okay, so that's how you perform an analysis. Again, you can do these computations yourself. And the second exercise that we'll be working with is the DR2 port network based on the circuit from the exercise 1. The value range of, we have to determine the value range of the resistor if the input is a triangular wave with 12 volts amplitude. Plot the current waveform and what is the maximum value for the current. So let's see how we can solve this problem. And actually I'm going to show you the solution to this exercise because I've already solved it. Solutions. If we go a little further down, this is the answer for point A of this exercise. No. So a little something like this. Okay, so I'm just going to copy it here. And let's explain what is going on. So in terms of current, we can write the current as being the ratio between the output voltage and the resistor. Again, this comes from none other than Ohm's law. So this thing comes from Ohm's law. And it is stated in the exercise that we have a triangular wave with 12 volts amplitude, meaning the maximum output voltage is 12 volts. And we are asked to measure the value range for the resistor, which we do not know. But what we do know is that this ratio should be smaller than the maximum current through the diode. Because of this here, the resistor should then be greater than 12 volts over the maximum current through the diode. The maximum current through the diode is given to us as well to be 50 milliamps. I forgot to write that. in the exercise. So it's given at 15 milliamps, and that is equal to 240 ohms. So this is how I solved this exercise. I'm not going to write the entire solution. You have it here, and in case you need it, you can take a screenshot and analyze it yourself. For the point B, actually for the point A, still, we have to consider a triangular voltage. So for that, these are the answers to the exercises that we're doing now, but solved in ORCAD, not LTSPICE. So to continue to solve this exercise, we have to change the input voltage to a pulse waveform with the following characteristics. So initial voltage minus 12 volts to 12, and it goes up to 12 volts because, like I said, this is the amplitude. No time delay. And let's have a rise time and fall time of 50 micro. They should be equal because otherwise we're not going to get a triangular wave. A pulse width of 0.1. Nano. And a period of 100 micro. 100 micro. Why 100 micro is basically the sum of the rise to fall time. And this is the time the voltage stays at its maximum value. So we have to have a very, very small value here. Okay, so this is our pulse waveform. I'll move this a bit to the left just because. And now we have to change the parameters of our analysis. So let me see. We're going to run up to 600 microseconds. And we're starting to save data at 0. So as soon as the simulation starts, with a time step of 10 micro. We click OK on that. You see that our analysis changes. We click on run, and now we should have a stable voltage input as a triangular waveform, which is exactly what we are obtaining here. It looks very nice, it looks very cool. This is the input of our circuit. However, at point A, we're asked to plot the current through the diode. So I'll delete this trace, right click on the diode, and this is the current waveform through the diode. And as you can see here, the maximum peak current, we don't even have to use a cursor to measure it, is 90 milliamps, which is the answer to question A. So 90 milliamps. Now let's plot the input and output of the circuit in terms of voltage and current, in terms of voltage. And what is the function of the circuit? Well, if I delete this and replot the input, make this green, as well as the output, which I'll go and turn it to a red line, you'll see here the green line is the input and the red line is the output. So what we have here, the input and the output, is what we call the VTC. And if you look closely to this VTC here, the voltage transfer characteristic, you'll see that at the output we only obtain the positive half wave of the input. Again, this is the input. This pink line that I'm about to turn into green. So this green waveform is the input and the red is the output. And you see at the at the output of the circuit we only have the positive half wave of the input signal. So this is why this circuit right here is called a positive half wave rectifier. You can see the VTC here as well. And because only the positive point of the only the positive points of the input signal are found at the output, this is a positive half wave rectifier. And you'll see that it's not a straight perfect combination between the two. So if we zoom in a little, there we go. I put a cursor on the output at exactly 150 micro. We have a voltage of 11.14 volts. And at the input, $11.98. And if we make a small calculation, so 11.98 minus 11. I think it was 11.14, but let me make sure that is the case. 11.14, okay. We get a 0.84 difference between the two waveforms. So this 0.84 that we obtained here is nothing else than the threshold voltage. If we were to simulate the current, like I am going to now, of course it's not, we already simulated the current, but the VTH should be at 0.84. Anyway, now we have to repeat the points A and B for the reverse diode. This computation right here stays the same, nothing changes. The only thing that changes is the direction of the diode. So to change that, select the diode, Control R, and put it and place it the other way around. And what do you think will happen this time? Well, not much. The current is the same, somewhat. You see that the current is still a maximum of 90 milliamps. So again, we only have one current, and this current does not change. But what does change is the input and the output waveform. We run the simulation again. At the input we have this signal, and at the output we have this. So the blue line is the output and the pink line is the input. And this time we see that only the negative half volt voltage values are sent to the output. This means that in opposition to the first circuit, this is a negative half wave rectifier. And here. Okay, because only the negative values are being sent to the output. And I think with that we are done. So go ahead and try and solve these exercises by yourselves. Next time we're going to go over a couple more circuits, 2 more circuits that I want to discuss with you. And then we'll see what we'll do next, because our discussion about the diodes does not end here. It's a discussion that will be that will take a big amount of time, but this is the starting point of our discussion with the DR2 port networks, which are very, very important, and I would like for you to know them. So we're also going to discuss, I think probably next time, we're going to discuss about voltage limiters and clamps and how they act in a circuit, as well as the DR2 port networks, this time with a load resistance attached. So rather than this simple circuit that we have here, we're also going to have a load resistor called this RL that will be attached, and we'll see what happens with this load resistor and how it influences our analysis. With that being said, thank you for watching, and I hope you have a great day.